Okay, one of the harder derivations in the course is to show that d sine theta is equal to m lambda for the bright bands in the two-slit pattern. So they'll normally give you something like this and say, show that at a point P somewhere up here, that's what the formula is for bright bands. So the first thing to do is do some constructions there from these two slits, because they're going to travel different distances the waves from there to get to point P. Okay, so if we do that first, there's your constructed lines. And what we're going to show is the path difference between these two is going to be related. So if we do a construction here, we're drawing that so that this distance here is the same as that distance. And we can put some labels in here as being A and B, if you like, and C. And what we're trying to show here is to the point P here, point P, all right, we're trying to show that the distance AP is the same as CP. Those two lines are the same, so we're drawing like that. And so that means that the path difference is here. The path difference, the extra distance travelled from this lower set of waves compared to that one, is going to be equal to BC, or you could call that X, I suppose you want to sort of call that little distance in there X. So you get some marks for identifying the fact that you understand that there's a path difference between one beam and the other, or one wave and the other, and this one will travel further to a certain point P on the screen. It could be any point. Okay. Now the tricky part here is to sort of try and show that this triangle here has some relationship to the big triangle. Now, there's a large triangle here, like that, to that angle there. This is your theta here that they've talked about in the equation, all right? And you've got a right angle triangle here. Right angle triangle here. So you've got one large red triangle there, theta, and you've got a right angle, there's your point P there, away from an origin, okay, there's your origin there. And here's your path difference in here. Now what we're trying to show is that this little triangle here in blue is similar to the large triangle I've just drawn. So we're trying to show this is approximately 90 degrees, this is approximately theta, and therefore you've got the x is equal to d sine theta equals m lambda. That's the actual aim here. So there's a few ways of doing this. I've actually seen 3 or 4 now. One of the easy ways, though, is to talk about being parallel lines. So because the length to the screen here is much, much, much larger than the distance between the slits D, because this is normally like 0.2, 0.3 millimetres, and the length could be anywhere from 30 centimetres up to a metre or a long way away. So that is much bigger than D. And because of that, you can actually say that these 3 lines here are very close to parallel to each other. Very close. If you imagine it's a very tiny set of slits there close together, and the screen's a long way away, these are very close to parallel. Now because of that, when you do this construction here to show a path difference, this is going to be very close to 90 degrees. Okay? And not only that, if you compare this blue triangle with the red one, if I just rotate the blue triangle round, you can actually see that one goes like this here. There's your D, there's your 90 degrees. This one here, now why is that theta? Well, it turns out that that one there is an alternate angle to this one here, which of course is very close to this one. Okay, so in here, that angle is the same as that angle, or this one here rather. Okay, so therefore the remaining angles must be the same of theta. Okay, so you can do a lot of mathematical work there, different ways of doing it to show that this little triangle in here is actually D, and it's got an angle there, theta, and you've got an angle there. So you can come up with a formula for this path difference then. Okay, and you look at it, what you've got is the sine of theta is opposite over hypotenuse, so therefore x, the path difference, is d sine theta. So there's lots of ways of showing that. That's not going to leave a lot of marks in terms of physics, because all you're doing here is trying to show, okay, we've got a triangle here, and this little triangle has got a path difference of d sine theta between the 2 beams. To actually get constructive interference, you need to argue some physics here. For constructive interference, path difference has to be a whole number of wavelengths. So the waves are right in phase and give constructive interference and that bright band. So what we're saying here is, i.e., the path difference, which is d sine theta, which you show with all that mass, must equal m lambda, where m is an integer. Okay, well, m equals 0, 1, 2, etc. And that's the gist of it. So if we look at an example of this then, how much do you have to do on the exam paper? So here's an exam, this is the 2012 exam, okay? So if you look at this here, the light source, you've got your single slit to go get coherent light at the double slits. Here's your screen a long way away. On the diagram above, draw the beams of light that travel from S1 and S2 to point P. So you're really just going to be doing straight lines there like that. So they're giving you a guide here to show this is what it's going to be about. Now it says indicate the path difference between the two beams of light. So I'd be going like this and say I'm doing a construction there. So these two are the same lengths to there. Okay? There is your path difference here. Okay? Now it says derive d sine theta equals m lambda for the two slit interference pattern, where d is the distance between the slits, which is here. Okay? And theta is the angular position of the m maxima. So here is the angular position here. That's what they're saying. Okay? So you can sort of see that's very similar to what I've just started to do. So how much would you need to work on there in terms of the maths? We have a quick look here. It's only worth 3 marks. So I wouldn't be focusing too much on the maths here. If I saw a lot more, I'd be trying to prove that these triangles are similar. Okay, but without that, can we do it easier? L is much greater than D. Okay, you've got angle A, B, C. Angle BAC is approximately equal to 90 degrees, theta, sorry. And angle BCA is approximately 90. And I wouldn't go too much into justifying that for only 3 marks probably. Okay. Now the key part here is that you say the path difference then. Now, if you look at this triangle then, the path difference x is going to be equal to d sine theta. Okay, you've got theta there, you've got 90, you've got x, so that's d sine theta. And this needs to be a whole number of wavelengths for construct of interference. That is, d sine theta has to equal m lambda, where m is equal to 0, 1, or 2, or 3. Okay, so that's the key parts of that. Okay, so that's a useful formula. Thank you.